All right, so you finished off a couple labs in the last couple of weeks. They seem to go well. Unfortunately, you weren't able to do them in the lab. It's a lot more fun when we mix the chemicals together. If we ever do get back to school this year, I'll let you do a couple of those labs or come up with a couple new ones so you get the fun of actually doing the lab and completing it yourself. But for now, I guess it's YouTube videos. So we're going to move on, and today we're going to look at matter. So what is matter? Matter is anything that has mass and takes up space. So that's excuse me, that's literally everything. The cell phone that you might be holding, it has mass, which means it has weight, and it's occupying space. A cup of water. The water in that cup has weight, it has mass, and it's taking up space. Even the air around you, you can't see it, but it has weight, very little, but each air molecule does have a little bit of weight, and it's taking up space. Now, all matter is made up of atoms, and atoms are these little tiny particles way too small to see. They're so small, in fact, that on the tip of a needle, the pointy end of a needle, you can have over 1 billion atoms. They're that small. So too small to see, but they are there. And when these atoms bond together, we get what's called molecules. So if you look at the diagram here, this very well might be a diagram for water. So this could be a hydrogen atom, or sorry, an oxygen atom. And if these two blue ones are hydrogen atoms, if they bond together, they form this thing. This is a molecule. A molecule is something with more than one atom. So this here could very well be water, H2O. So two hydrogens and one oxygen. So here we have hydrogen atoms, oxygen atom. When they bond together, we get a molecule. Now molecules are two or more, as I said, atoms combined together. So in fact, the oxygen that you and I are breathing right now, it's actually a molecule. Oxygen in nature, you won't find just one on its own. It will always bond with a second one. So the oxygen that you and I are breathing in right now is an oxygen molecule. It's two oxygen atoms stuck together, bonded together. I shouldn't even say stuck. And you are breathing out carbon dioxide. That would be one carbon atom and two oxygen atoms all bonded together to form a carbon dioxide molecule. Now there's different kinds of atoms, and we call these elements. And we find all the known elements on the periodic table. So here's an example of the periodic table. And these are all the known atom types. I quite often refer to these as the Legos of the world. So if you ever played with Legos as a kid, or maybe you still do, fantastic. You could take those Lego pieces, you could put them together and make a house. You could pull them apart, put them together in a different way, and you get a car. Pull them apart, put them together in a different way, and maybe you've created a spaceship. But you only had a certain amount of Legos in front of you. That's what everything's made up of. It's made up of these Legos that you're seeing on the screen in front of you here. And there's actually a couple more rows down here. This bluish seafoam colored row, it goes right in here, and they all get stacked on top of each other. And this light green row, it goes right in here, and they get stacked on top of each other, sort of 3D. But these are all the different Lego types, and we can put them together to make things. The oxygen that you're breathing is two of these oxygen atoms together. I talked about water. That's one of these hydrogens and two of these oxygens bonded together, and now we have water. The salt on your table that you put on your food, that is a sodium and a chlorine atom. Now, sodium is a soft, silvery, shiny metal. Chlorine is a gas. But when they bond together, they form something new. Just like you put a couple Legos together, they're just a Lego on their own, but when you put them together, they form something new, whatever you're making. So here, sodium and chlorine make salt. In the natural world, hydrogen, carbon, and oxygen are quite prevalent. So we talked about water, we talked about carbon dioxide. If we take 6 hydrogens, 12 carbons, and 6 oxygens, we get sugar. If we take hydrogen, carbon, and oxygen in a different form, in a different ratio, different numbers on them, we get vinegar. So totally different substances made up of these different elements. So hydrogen, and each of them is given a symbol. You can see that in the periodic table. So hydrogen is a capital H. Now helium is not a capital H because it's already used, so it's a capital H small e. If there's only one letter, it'll be a capital. If there's more than one letter, like aluminum here, it'll be a capital followed by a lowercase. Now sometimes the letters make sense, sometimes they don't. Lithium, Li, that makes sense. Sodium, Na, that doesn't make sense. Why isn't it S? Well, if you look over here, sulfur has already used up S. And if you look around the periodic table, there's some other ones that have S in a smaller lowercase letter, like cesium is, or sorry, that's not S. Strontium here, scandium, tin. Why does it have an S? It's not T. Well, some of these are also named after their Latin roots. So right down here, gold, element number 79. In Latin, gold is A-U-R-U-M, aurum. And so gold, the two letters are taken from the Latin root. You'll notice around a bunch of them are silver, agium, and lead here, Pb. Plumbum is its Latin root. So some funny names there, but that's why some of them have different letters. The letters are already used, so they had to go to different roots of the name. So when we take 2 atoms of hydrogen and combine them together, as I mentioned, 2 oxygens together is an oxygen molecule. A oxygen and 2 hydrogens bond together is a water molecule. And so that's the difference between elements in atom form and molecules. Particle theory. So everything is everything is matter. Matter is anything that has mass or weight and takes up space. And everything is made up of little tiny particles. We talked about that already in the last note. Everything's made up of these different atom types. Now, those atoms act in a certain way, and that's called particle theory of matter. And there's 5 main parts to it. The first part here is that everything is made up of tiny particles. And in between those particles, there is empty space. So your desktop is made up of particles. Vinegar is made up of particles. Air is made up of particles. Water is made up of particles. Everything is made up of particles. In between those particles, there's nothing. It's empty space. It's not air in between them. It's nothing in between them. Different substances are made up of different particle types. So going back to our periodic table, gold is made up of gold particles. Boron is made up of boron particles. Potassium is made up of potassium particles. And so different things are made up of different particle types. Particles are always in motion. So those little particles, if you can see down here in these beakers here, they're always moving around. Sometimes, like in this molecule here, it's zipping all over the place, and that's indicated by this arrow. If you go to the liquid or solid form, you can see these little vibration lines. So that's showing that, especially in a solid and liquid, the particles are constantly vibrating, shaking, and especially when it gets to gas form, then they actually start to move around as well. Particles move faster as they warm up. So as you warm something up, the particles start to move faster. They vibrate faster, they move around more. And particles have gravity. They attract each other. They want to join up and form a particle. So going back here, they want to do this. When you have particles on their atoms on their own, They want to attract to each other and form something new. Now, here we have particles in 3 different states of matter: solid, liquid, and gas. And I want to point out a few things about them. One, so usually in its coldest form, something will be solid. So if you think of water particles, when you cool them down below 0 degrees, they become solid. It becomes ice. It freezes. If you take liquid candle wax and you cool it down, it will become solid candle wax. If you take a molten metal and you cool it down, it'll become solid metal. So usually when things are the coolest, they are in solid state. And we know that when things are cooled down, that the particles move slower when it's cold. And when they cool down and they start to move slower, they're able to attract each other better. And so in solid form, these particles have attracted to each other and they're stuck to each other really, really tight. And that's why they're able to hold their form. So you can imagine if this is, these are water particles. We've cooled it down to below 0, below freezing. And so those particles have slowed right down. They've attracted to each other nice and tight. And they can hold themselves in the form of an ice cube. So when I put an ice cube into this beaker, it stays in the shape of an ice cube. Those particles are attracting to each other and holding each other. Once we warm them up, they start to vibrate and move around a little bit more, and they aren't able to hold on to each other as well, so they break apart. And now you can see the water, even though it's really close together, the particles, it's not holding its own shape anymore. It's actually taking the shape of the container. And if we were to pour this into another container, it would then take the shape of that container. If we continue to heat it up, then the particles move around faster and faster and faster, and there's less gravity holding them together, and they're able to spread out even more. And so that's like the air in the room around us. It's taking the shape of the room, and those air molecules are moving all over the place. So in solids, they're close together and they attract each other strongly. In liquids, they're still close but have some slight separation, and in gases, they're far apart. This can all be explained how substances melt. Particles moving faster and faster with heat push and bounce off each other, and they get more space in between, therefore losing their grip on each other and going from a solid to a liquid. And if they keep getting heated, they end up going into a gas form. So particle theory can also explain why gases are easily compressed. So when I go scuba diving, they'll take a room full of air and they will squish it all up. They will compress it and they'll put it into a little tank on my back. The reason they can do that is air has so much space in between that they can push all those particles together and fit a whole room's worth of air into a small scuba tank on my back. Can't do that with a liquid or a solid. You cannot take a glass of water and compress those molecules down and make them any closer together. And you definitely can't do that with a solid either, because they don't have the room in between them. So there we go. A couple notes, ladies and gentlemen. Make sure that you've either copied these down or you print them up or put them into your, save them onto your computer so you have a copy of them somehow to refer back to. Some of these notes might be handy next year in grade 10 science when you're doing chemistry again. And I'll be following this up with a worksheet as well.